This self-portrait of the Curiosity rover, made by combining many separate images, shows the dry, barren surface of Mars today. In fact, the surface pressure is so low that liquid water is not stable on Mars today. If you lived in a pressurized Mars habitat and took a cup of water outside, wearing a spacesuit, of course, the liquid water would rapidly either freeze or evaporate, or some combination of both. But abundant evidence indicates that Mars was not always like this, and that surface liquid water was stable in the past. For example, this image from the Curiosity rover shows layered sediments that were likely deposited over time in a lake. Orbital images also show clear evidence that Mars once had rainfall, lakes, and rivers. This image, which is color-coded to make its features easier to see, shows an ancient, now dry, river delta. In fact, Mars may once have had enough liquid water for its low-lying northern hemisphere to have been a vast ocean, as illustrated in this artist's painting that shows what Mars might have looked like some 4 billion years ago. So why did Mars undergo such dramatic change from this watery past to its cold, dry conditions today? Before we answer, first consider a different question. In order for Mars to have had stable liquid water in the distant past, which of the following must have been true? Did it have more oxygen and nitrogen, or more water ice, or a thicker atmosphere with a stronger greenhouse effect, or more heat from molten lava? The answer is C. In order to have had rainfall, lakes, and rivers, Mars must have been much warmer and must have had a much greater surface pressure. Both of these can only have happened if Mars had a much thicker atmosphere to create the greater pressure and a much stronger greenhouse effect to create the warmer temperatures. This fact brings us to the leading hypothesis for why Mars changed. Let's examine the hypothesis, as shown in this figure. Like all the planets, Mars should have had a hot interior when it first formed, and this heat allowed it to differentiate to make a metal core surrounded by a rocky mantle and crust. The internal heat would have driven volcanism and outgassing, giving Mars a substantial atmosphere. The atmosphere would have been much thicker than it is today, and because the outgassing would have released greenhouse gases including carbon dioxide and water vapor, the greenhouse effect would have been much stronger. Meanwhile, like Earth, Mars had a core of molten, convecting metal. This convection of electrically conducting material, combined with Mars's relatively rapid rotation period of a little more than 24 hours, should have given Mars a global magnetic field. The magnetic field, in turn, would have given Mars a magnetosphere that protected its atmosphere from the solar wind, just as Earth's magnetosphere protects our atmosphere today. In other words, the young Mars may have been similar to the young Earth. But unlike the case for Earth, conditions did not remain so hospitable, and our hypothesis traces the reason to Mars's smaller size. These pictures show Earth and Mars to scale. The size difference is important because just as a hot pea will cool faster than a hot potato, a small planet's interior will cool faster than that of a larger planet. Earth is large enough that it is still nearly as warm inside as it was when it was born. In contrast, Mars should have cooled relatively rapidly. By about 3 billion years ago, Mars's interior should have cooled enough that core convection ceased. This, in turn, would have greatly weakened Mars's magnetic field and magnetosphere, leaving its atmosphere vulnerable to being stripped away by the solar wind. The cooler interior would also have meant much less volcanism and outgassing, leaving no way to replenish gas that was lost from the atmosphere. Much of the gas that remained presumably reacted with surface rock. For example, reactions with oxygen gave Mars its rusty red color. Other gas condensed to make the polar caps. With its atmosphere dramatically thinned, Mars was left with only a very weak greenhouse effect and the cold, dry conditions we see today. Returning to our full summary figure, the leading hypothesis suggests that the key to Mars's fate was its relatively small size, which led to the chain of events through which it lost most of its early atmosphere. If this hypothesis is correct, we should see evidence for it in the precise way in which Mars still loses atmospheric gas today. The MAVEN spacecraft, shown here as it would look as it orbits Mars, was designed to measure the escape of gases and thereby put our hypothesis to the test. These ultraviolet images from MAVEN show the distribution of carbon atoms, oxygen atoms, and hydrogen atoms around Mars. All the atoms extend to altitudes high above the surface, where they can be lost to space, with hydrogen extending the highest because it is the lightest weight gas. The MAVEN results show that Mars really is losing atmospheric gas through the expected processes, though more work is needed to fully quantify today's loss rates and extrapolate them back in time. To summarize, geological evidence shows that Mars underwent major climate change in the distant past, and results from MAVEN tentatively support the idea that this climate change occurred for the reasons illustrated in this figure.